Hello, welcome to our lesson on isomorphism, planar graph, and graph color. So in isomorphism, this is where two graphs are isomorphic if there is a one-to-one correspondence between the vertex sets having the property that whenever two vertices are adjacent out of the graph, the corresponding two vertices are adjacent in the other graph. And it's called an isomorphism. The way to denote it as two graphs being isomorphous is by this particular symbol I have here in black. So to check both of these two sets here, set the graph for isomorphism. Let's call this set up to the first one here. So going from left to right, the vertex A in the graph on the left has a one-to-one correspondence with vertex 3 on the second graph. B has a one-to-one correspondence with 1. C has a one-to-one correspondence with 2. And D has a one-to-one correspondence with 4. So this first set of graphs here, these two would be isomorphic. And the second one here at the bottom, there we go. A has a one-to-one correspondence with 4. B has a one-to-one correspondence with 1. C has a one-to-one correspondence with 2. And finally, D has a one-to-one correspondence with 3. And again, that's all based upon the vertices that are adjacent and either of the two graphs. The same ones have to be correspondent on the other graph as well. So yes, this one's also isomorphic. And by the way, I should probably make note that while I did write these one-to-one correspondences here, these are not necessarily the only one-to-one correspondence. So there can be more than one pairing of these. For these two, to check to see if these are corresponding or not for an isomorphism. So we could see in the first graph on here that we have, and already over here on the side, A being adjacent. A is adjacent to both C and F. And based upon that, the one that actually corresponds with on the second graph is to the point of J here. A actually corresponds with J. The next one here is that B is going to abbreviate adjacent every single time I write this. We have so many. B is adjacent to G and to G. And the one that corresponds with on the second graph is this point here of N. So B corresponds to N. Likewise, point C, vertex C is adjacent. We may know to vertex A and to vertex C. And the correspondence with C on the second graph on here is where point K, vertex K. So with that said, for D, D is adjacent to, this would be C, yeah, C is adjacent to B, E, and F. The three of us with that one. So the correspondence in the second graph to the point D, to a vertex D, I should say, having three adjacencies. Then for E is adjacent to C. Yeah, E is adjacent to C, D, F, and Z. So this one has 4. So the one that E is correspondent with on here is going to be L, which is actually 4. Likewise for F, it's adjacent to, this would be A, D, A, D, and E. Again, this one has 3. So F is going to be adjacent to the point I. And then the last one, I'll just write that one over here since I have no room on the side. For G. G is adjacent to B and C. And the last correspondence for G is going to be M on the second graph. So yes, indeed, these two are indeed isomorphic. So with that being said, it should also be noted that due to these being adjacent, that provides us this isomorphism. So now this idea of a planar graph. A graph is planar if it is isomorphic to a graph that has been drawn on a plane without any edge cross. Otherwise, the graph is non-planar. So this first one here is indeed planar. There's absolutely no edge cross. No edge cross. And the second one, there's also no edge cross. No edge crossing. So as predicted, this one is indeed planar. And this last one, this one does have an edge crossing, right? But it's avoidable. This one actually is also planar. And to help me identify this, I'm going to call this graph number 2 and this one number 3. This third graph is indeed isomorphic to the second one. So because of that, it is indeed planar. Now, this idea of a graph coloring. A graph can be colored if a color has been assigned to each vertex in a way that adjacent vertices have different colors. So, with that being said, I have this cube on here, and some of these did not, unfortunately, go closely, but these vertices here are supposed to be connected. There we go. So with that being said, we can color this, right? So we could do this as red, blue, green, blue, green, orange, blue, and red. So that would give us a total of 4 colors. And that works. As you can see, none of them violate this idea of coloring it, so those are fine. But is it necessarily the smallest, right? And we just did 4 on that last slide. This idea of a chromatic number, mind you, of a graph is the smallest number of colors with which it can indeed be covered. The chromatic number of a graph is denoted by F, and based upon this cube, which again, edges did not show up on here. There we go. The chromatic number for this one is actually going to be a value of 2. And how would that look for this? Well, it's red here, the blue here,
red over here. And then for over here, we have blue, red, and then red and blue. So it can indeed be colored by those two. So because of that, 2 would be our chromatic number for this. Then the chromatic number for these two, for the one here on the left, this one's going to be 3. Now, why is that? I'm going to do red, blue, red. For those 3 verses, down here we have green, blue, and red for vertex F there. And over here we have blue, red, and green. So that way we don't have any of those adjacencies. Again, that's the smallest number it could be colored with. The one on the right, the smallest one for this one would be 3 as well. It should be, by the way, noted that both of these graphs are pointed, which is also a important note to make. This one on the right, though, can be colored with red, blue, green, blue, red, and green. In that particular order. For these two, we want the chromatic number for these. This one right here is 4, unfortunately. This one is 4. And the reasoning for that is because this would be red, blue, green, and because of those adjacencies, we have to use a 4th color over here. Let's call it orange. So this one here is 4, and this other one right here, this one would actually have a chromatic number of 2. And all the ones here on top can be colored red, because even though those points are right next to each other, they are not connected with any edges. And down here, we can call this blue. Again, for the same reason, they are not connected by an edge. So that's fine for that. Both of these are actually non-pointer. So with that being said, right, do we have a maximum number for this? And kind of. The 5-color theorem says that every planar graph has a chromatic number of that's less than or equal to 5. And the 4-color conjecture is every planar graph has a chromatic number of less than or equal to 4. That 4-color conjecture, however, has not exactly been proven in all cases. So it's certainly possible that some of them do, but it's also possible that there's others that might not. And it's one of those open cases in mathematics right now, for that particular conjecture for that. Let me know if any of you have any questions or concerns. Thank you.